using with at most 3k vertices. Essentially, we said that if the graph has more than 3k vertices, I'm using matching, we can find a crown. And once you have a crown, we can do some crown reduction rule and get rid of the crown and keep applying it. So the process stops. Either you say there is no vertex cover of size at most k, or you will find kernel with at most 3k vertices, right? So today we will improve that to 2k vertex kernel. Essentially what we are going to say is that if you have more than 2k vertices, either you will say that there is no vertex cover of size at most k by giving a witness of k plus 1 size matching, or we will find a crown. Okay. Now this one is going to be using linear programming. So let's recall the integer linear programming formulation of vertex cover. Right. So you are given this so the integer linear programming is what do you want to minimize? So it has a variable for every vertex and you want to minimize summation xv, right, and the interpretation is that the variable is set to 1 if it is in the solution and 0 otherwise. So you want to minimize the number of vertices you pick into your solution subject to the constraint for every edge either xu or xu or w must be there in the solution, which can be written in this linear inequality xu plus xw at least 1, and your xv's are in 0 1. Okay, so this is a, if you have only these two constraints, it's a linear program, it's a linear objective function with linear constraints. With this extra integrality constraint, it becomes an integer linear program. This is an NP complete problem, so you can't solve it efficiently. So what are we going to do with it? Well, we will relax this constraint and write this. It means we are going to allow some fractional values for xv, which we don't know how to interpret it for the vertex covers, because suppose, so the advantage is this has become a pure linear program which can be solved in polynomial time. Okay. So once you have this linear program, solve it in polynomial time and you will get these fractions and we are going to somehow interpret these things. Okay. And notice that you also don't need this constraint, right. We have discussed this because there is no reason for any variable to go above 1, because it is a minimization objective function and this is the constraint you want to satisfy. If any variable goes above 1, bring it down to 1, it will still satisfy all the constraints and you will get a better objective function. So you don't even need this constraint if you are trying to minimize this. Okay. So this is a linear program and we are going to solve it, and okay, so let x star be, let's call this be the optimum solution for the LP. Okay, and let's look at the following set of, okay, look at the summation x v star v in v. If this is more than k, what can you say? Notice that the integer linear program exactly models the vertex cover. So the objective function for the integer linear program gives you the minimum vertex cover size. Once you relax it to linear program, your objective function may actually can become even smaller, correct? Because you have relaxed it. Whatever was a solution continues to be a solution even now, but your objective function may become smaller because you allowed some fractional values. So let's make this observation that opt of this LP is less than or equal to opt of this integer linear program. Agreed? Because any solution for this is also a solution for linear program. Right? So if you have something which optimizes this, that's also a solution here. So there is no reason this would be bigger. It's a minimization problem. By relaxing, you might get this. And what is this? This is the size of the minimum vertex cover, right? Because okay. So now if the opt of the LP value is bigger than K, what does that mean? There is no vertex. That means the minimum vertex cover size is bigger than K. And I am after a vertex cover of size at most K. So I can stop and say no, right? Then G is a no instance. So now let me look at these three sets. Set of all V in V such that XV is less than half, greater than half, this is a partition of my vertex set. Suppose these two sets are non-empty. So everybody in your optimum LP gave you, it put the variable value to be equal to half, okay, or actually even without it. How many vertices are here? Can you give me an upper bound for this? Given this, how many vertices can there be here? At most 2k, right? Because total sum is at most k, so exactly equal to half is at most 2k. That's going to be my kernel. Somehow I am going to get rid of these sets. So if these sets are empty, you are already done. If not, I am going to give you a crown. Okay. So what is a crown? I claim that this partition is actually a crown. Okay, we'll try and prove this. But now do you see that if once I show that claim, if these sets are non-empty, if these sets are empty, then you are already done. In particular, if C is non-empty, then H must be non-empty, right? Do you see that? Assuming there are no isolated vertices and so on. Assuming there are no isolated vertices, if C is non-empty, H must be empty. H must be non-empty because there is some edge going out of it where the other endpoint must get value greater than half because I want to satisfy this constraint, right? Okay, so okay, so once you have a crown, you can reduce it. So why is this crown, right? Let's give a proof of it. Recall the properties of the crown. The first thing is that G of C is this set induces an independent set. Is that obvious? Okay, why? Yes, if there is an edge inside, both endpoints have value less than half, then how will it satisfy this constraint? So because that constraint is satisfied, G of C is independent. Good. What are the other constraints? There is no edge between C and R. Is that clear? Why? Same reason, right? If there is an edge between one vertex in C and another vertex in R, this guy's value is less than half, the other guy's value is equal to half, both cannot be, they don't add up to at least 1. Okay. The third property is the more interesting, challenging one to show. What is the other one? What's the property of a ground? There is a matching that saturates H, right? So I will use Hall's theorem to show this. Okay, so look at this bipartite graph, the graph between C and H. In this, okay, in this graph, which I gave this notation, C and H are two parts, and you are looking at only the edges across, right? Note that H is not necessarily independent, so there may be edges, but those edges I am not looking at to claim my matching. I am only looking at edges across. So if I want to use Hall's theorem, what should I show? What do I have to show?
You have to show that for any subset of vertices in H, the union of the neighborhoods is
at least H, right? So we will show for all S contained in H, neighborhood of S intersection C is greater than or equal to S, right? Then the claim will follow from okay, so suppose not. Here is where I will use the optimality of the linear program. Suppose not, what does that mean? There exists an S contained in H such that neighborhood of set intersection C is strictly less than cardinality of S. So I have my set S here, this is my H, then I look at my neighborhood of S, this is my C, and somehow this set is smaller than that. Remember, everything here is value greater than half and everything here is value less than half. So the idea is the following. So what I am going to do is, I will increase, so I will find some epsilon so that I can decrease the value of each of these guys by epsilon and increase these guys by epsilon, still make sure that my LP constraints are satisfied. Since I have increased less than what I have decreased, because this size is less, I would have gotten a smaller solution which contradicts the fact that what I have is an optimal solution to LP. Okay. So, what epsilon should I choose is the question, and so what is the epsilon I should choose so that I can decrease all of these guys by epsilon, don't touch anybody else, increase the corresponding all these guys by epsilon, the same epsilon, and I want to argue that I will meet all the constraints of the LP. Okay, so what epsilon should I choose? Okay, so here is where xv is in S or v is in S. So each of the values are strictly more than half, right? So I will find how much more than half each one of this and look at the difference and take the minimum among them. Okay. So now let me define my new solution, which I will show it to be less than the optimum solution, the objective value. So now my xv prime would be xv minus epsilon for all v in S, xv plus epsilon for all v in n of S, and xv or whatever star, right? Okay. Now this should be obvious, right? Clearly summation xv prime is strictly less than summation xv. Is this obvious? Why? So for each of this I have reduced epsilon, for each of this I have increased epsilon, everything else remains the same, right? So whatever I have since neighborhood of S intersection C is strictly less than cardinality of S, what I increased is strictly less than what I decreased. So overall there is a net decrease. So this is strictly less than this. If I now show that this xv prime still satisfies my LP constraints, then I will have a contradiction, because this was the optimum LP solution, I have produced something smaller. So now we will argue that, I mean again that is fairly obvious, that let us x prime equal to xv v or xv prime is a feasible solution for the vertex cover LP. Okay, let us check. So there is also this R, right? These are the equal to half guys. So let's just, all we have to do is check for every edge whether the xu plus xw is greater than or equal to 1. Any edge inside, no problem. I have not touched anything, they remain 1. Any edge like this, no problem, because this is half and this never goes below half, because it is always strictly greater than half, and I ensured by picking the minimum of this, at best maybe there is one vertex which will become half, or maybe there are several vertices which will become half, but it never goes below half. So any edge of this type, half is fine. This is independent anyway, so whatever you do, there are no edges. So you really have to worry about edges inside and edges here. Edges inside again no problem, because they remain greater than or equal to half. Each vertex value remains greater than or equal to half, edges inside no problem. Edges across like this, any edge like this, no problem, because you have decreased it here and increased it, or decreased it here, increased it here, so they are offset. There are no edges from here to here or anywhere else. There are other kinds of edges, well, I didn't touch the values, previous values, so they remain feasible. Agreed? So what I have produced is a feasible solution to the linear program whose objective value is strictly less than what I claim to be optimum, so that is a contradiction. Contradiction to what? Contradiction to this, that there exists some S such that whose neighborhood is strictly less, so there is a matching that saturates it. Right, so now we have found a crown. From what we saw for the crown reduction rule for vertex cover, I can safely pick all of these vertices into my solution, delete this and work with the remaining thing. And if this size, yeah, and this is less than or equal to 2. So this is like a one shot now. You don't, we're not even applying this again. We get one crown, reduce it, and we are done. Because this is at most 2k anyway. So we find a crown, reduce it. If these guys are non-empty, then this is what it is. So there are nice corollaries of this. So what have we shown? We have shown this is a famous Nimhauser-Trotter theorem. In 1970s, 80s or something, which essentially shows that there exists an optimum solution such that S contains H and it is contained in R union H. There is an optimum solution that contains all these vertices and it does not contain any of these vertices. Note that this immediately, so this immediately also gives you a 2 approximation algorithm for vertex cover, right? You solve the LP, pick all those which are greater than half into the solution, delete these guys. Now what is left is everybody is equal to half and you know that the integer optimum is less than or equal to 2 times this. Okay, so even if you produce all of these vertices as your solution plus, so let me just write. So this is okay. Nimhauser-Trotter didn't talk in terms of crowns, but here is a proof of Nimhauser-Trotter theorem. Okay, so you can think of it as a corollary one, which because of this theorem follows. H union R is a 2 approximation algorithm for vertex cover. Okay, corollary 3, which we will prove, there exists an optimum solution for the LP, not for the vertex cover integer part, but the LP where, so I won't call it corollary 3, let me call it a new theorem, but this is also Nimhauser. The variables values are in 0, half, 1. Okay, I will prove this. So what I am saying is, there is a reason why this is useful. So our 2K vertex kernel is done, by the way, right? I mean, we are moving ahead on learning more from the LP thing, because our 2K vertex kernel is that if any of this sets is empty, you take, this is a crown, collect all of this into your solution, remove these. Now what is left will have size at most 2K, or in between you've learnt that this is true and it's a no instance. And all we did was to solve the LP and collected those which are less than half, greater than half, equal to half, and that's it. Now, even though solving LP is polynomial time, it can be a bad polynomial time in general, but then it turns out for the vertex cover LP you can solve it very efficiently using bipartite matching. Okay, so I am going to explain that, and as a consequence of that this will follow. Okay, so what is this saying? Take your vertex cover LP, solve it. The values can be anywhere between 0 and 1, but there is an optimum solution to the linear program, not the integer one, but the linear program, where the values are not all over, either 0 or a half or 1. That's all. Okay. So there is a combinatorial way of solving the vertex cover LP using matching, and that will, as a bonus, we will get this. Okay, so how do I solve that? That's another interesting, useful thing to know. So solving vertex cover LP. So we have given this graph GB. Construct the following bipartite graph. Where you will have V1, V2 and E, and this V1 and V2 are nothing but V, okay. 2 copies of your vertex set. So I have my G, and I will make 2 copies of my vertex set, and whenever there is an edge UV, I will have U1, V1, U2, V2. I'm going to add these 2 edges. Okay, is there a name for it? Join something? No. G1 cross G2. Okay.
Here edges are there or
no? No edges. So it's not G1 cross G2. Okay. Yeah. So this is a bipartite graph. Okay. So let's call this bipartite graph maybe B. But whenever there is an edge here, you will have this two edges here. Find the minimum vertex cover in B. Let's call it S. In bipartite graph, you can find this in order m square root of n, find a maximum matching, minimum vertex cover, you can find all of that. Now this minimum vertex cover in this bipartite graph may pick both copies of a vertex, or one copy of a vertex, or no copy of a vertex. Based on that, I am going to decide the corresponding LP value to be 0, half or 1. Okay. So set xv equal to 1 if V1 and V2 are in S, half if only one of them, and 0 otherwise. The claim is that what I have produced you is an optimum solution to the vertex cover LP. With what is its value? What is this? This is exactly this. Right? Because if 2 copies are there, I'm going to set it to 1. Only 1 copy, I'm setting it half. If it's 0 here, 0 here. Okay, so I have to show that it is actually a feasible solution to the vertex cover LP in G, and it is an optimum solution. So, vertex cover LP of G. Right. So, this gives you another way to solve our LP. You want to solve the vertex cover LP, I construct this bipartite graph, find a minimum vertex cover here and get my solution, and put it in values here in my LP, and that's another way to solve the LP without really going through all this matrix, huge algebra thing. You just solve this matching, and it also shows this statement, right, because I have produced an optimum solution where the values are 0, half, 1. Okay, so first, is it obvious that it's actually a feasible solution? Does it satisfy all the constraints, right? So, you pick any edge UV, I mean that's obvious, right, because your S is a vertex cover in the bipartite graph. So, if you pick any edge UV, you would have had U1 V2, U2 V1. Your vertex cover S will cover both these edges, right. So, it should certainly pick at least 2 vertices out of this 4. So, when you divide by 2, at least 1 must be true here, right. I mean, when you get okay, if you have 0, 0 or 0, half or half 0, these are the possibilities where this constraint would be violated. Let us see, if 0, 0 is certainly not possible, because that means all of these guys are 0, but S is supposed to be a vertex cover, right. From S I got this, S is a vertex cover for this bipartite graph, so this is not possible. What does 0, half means? That U1, U2 are not picked, but out of V1, V2, sorry, this is what it is. So, 0, half means U1 and U2 are not picked. That forces me to pick both V1 and V2. So, this must be 1 then. If one of this is 0, the other one is 1. Right? One of this is 0. That means that U1 and U2 are not picked in my vertex cover of the bipartite graph. Then V1 and V2, that means the 2 copies of V must be picked. So, other guy must be 1. And similarly, if one of this is half, the other guy must be at least half, because suppose U value is half, that means from U1, U2 I have picked, let us say, exactly one of them. That is why I got U got half. That means that to cover this, I have to pick this, I mean, so U is not picked, so this is forced. So, V1, V must be at least half. If U is half, V must be at least half. Okay, you seem confused.
It is half or condition is.
So, this is my, this is the way I obtain this. So, all I am saying is, suppose
0, 0, 0, half 0 and
half is fine, right? That satisfies my constraint. So I claim that none of this is possible. If any one of this is 0, if any one of this is 0, so u is 0 means these two are not picked in the solution. That means that these two are picked in the solution because this has to cover this edge, so this must be 1. This 0, this implies 1. And if any one of this is half, that means from u1, u2, let's say I picked only 1, u2 is not picked, that forces v1 to be there. So from this it must be at least half. So the sum will at least be 1. So that means that my xv is a feasible solution. To the vertex cover LP of the graph. Now I want to show that it is actually an optimum solution as well. And the way I am going to show is that any other solution is of size at least this much. Since it's a minimization problem, this will be the optimum. Okay. So, to show optimality, let YV be in B any solution to LP vertex cover of graph G . Then, so now let's somebody has given me a solution to this LP. Okay, so that means that for every vertex there is a value. My LP gave me some value. I will give that value to both copies, right? So whatever xu is, I am going to put here that value here and look at the bipartite vertex cover LP value. Okay, so I take the LP value from the graph, the vertex cover LP, somebody gave me this LP which is y. From here I am going to produce a solution for the vertex cover LP for the bipartite graph. How do I do? I am just going to put the same value, copy it in both these copies of the vertices. I claim, okay, let's look at that, right? So let Z V1 is equal to Z V2 equal to YV, and consider this Z variable values on this bipartite. I claim that it is a feasible solution for the bipartite vertex cover. That should be obvious, right? Because for each of these edges the value is at least 1. If you look at the vertex cover LP for this, the edges are this, but this is basically XU, this is XV, and this sum is at least 1. That's how you got the XU values. So then Z VI I equal to 1, 2, V is in V is a feasible solution to the vertex cover LP of the bipartite graph P. Okay. It's a fractional solution. It's not because these LP values can be fractions. It's a fractional solution. It's a feasible solution. And so summation ZVI is greater than or equal to summation ZVI star, right? Look at the optimum solution for the bipartite vertex cover. It's a minimization problem, so this is greater than or equal to that. Optimum is an integer, we know. In fact, we know what is optimum. Optimum is this, right? Because it's a bipartite graph. So here we use the fact that in the bipartite graph, the optimum value of the LP is integer. So this is exactly equal to cardinality of S, right? Because it's a minimum vertex cover in a bipartite graph. It's a fractional vertex cover minimum, but we know that in bipartite graph, the optimum is actually an integral solution. So this is equal to cardinality of S. But this is equal to 2 into summation YV, right? Because every YV is repeated 2 times. But what is this? This is 2 into summation XV. So what have I shown? If you cancel this 2, for any optimum solution to the LP, YVs, their sum, which is the objective value, is greater than or equal to the XV I generated. So XV is the optimum, right? So this implies it's an optimum solution to LP vertex cover of G, which in turn proves this theorem. So I went to bipartite graph, solved minimum vertex cover there, which is doable in polynomial time, and then retrieved an LP solution from there, and I argued that that LP solution objective value is less than or equal to any other LP solution you can come up with. So that's an optimum solution for my graph. Okay, so that proves that theorem, which says that there exists an optimum solution to my LP where the values are 0, half, 1, and also says that such a solution can be found in by finding a maximum matching, whose current best time is something like m root n times. Okay, good. So this Nemours-Trotter theorem is known. All this was all known 30 years ago, before parameterized complexity came into picture. And the k-square kernel stayed for a couple of years until somebody noticed that, hey, we can apply this old theorem, do this reduction and get some 2k vertex kernel. Okay. Later, when we will do actually branching algorithms to show fixed parameter tractability, we will improve this even further to 2k minus log k. But the number of edges remains k square, because remember, finally what survives is those which have values equal to half, and it could be all the vertices and it could be 2k vertices, there may be edges all across. Okay, good. So that for now is we'll stop here on the vertex cover, and maybe even on the kernelization more or less. I want to talk about the related problem of feedback vertex set. Set it up, we won't actually give the good kernel, and then move on. Okay. So here there are two versions, both in undirected and directed graph. Directed graph version is much harder. So what is the problem? Your input is some graph, parameter is k. The question is, does there exist a subset contained in V such that cardinal div S is less than or equal to k and G minus S is acyclic? So the vertex cover question is there a subset S such that G minus S is an empty graph, right, without edges? S should cover all edges. Here we want S to cover all cycles. This, the same formulation works for directed or undirected graph, except in the case of directed graph, when you say acyclic, it should be devoid of directed cycles. Okay, you might have undirected cycles, but in the directed sense, it should be acyclic. Now, what do we know? Coming up with any kernel is quite hard here. Okay, I mean, at least for a vertex cover, quickly using this bus rule in like 3 sentences, 2 rules, you got a kernel with k square vertices and edges. Here, I don't know, even k cubed or k power 10 is not that hard. Okay, you need some work. K squared requires some nice combinatorial theorem, Erdos-Galai theorem, and we will use that, and expansion lemma, some combinatorial tools to do this. So we won't do it today, maybe next week or the following week. For directed feedback vertex set, kernel question is open. It's been a long-standing open problem here for whether there is a polykernel. Note that we now have some machinery to show that polynomial size kernels are unlikely. We will get to that sometime when we talk about hardness. So we don't know either way about this. Okay, so what we will do is we'll see why it's a problem. We'll get started with coming up with the kernel. What are some simple reduction rules we can come up with? So let's stick to undirected graph. So what are some simple rules? You want to cover all cycles, right?
Get rid of vertices with degree less than or equal to 1.
Okay. Delete vertices with degree less than or equal to 1, because they are not part of any cycle. They are not going to cover any cycle. So really, to truly argue the correctness of this, I should say that the resulting graph has a feedback vertex set of size at most k, if and only if the original graph has a feedback vertex set of size at most k, but that's fairly obvious. What do you do with the degree 2 vertices? Also, a feedback vertex set has no reason to pick a degree 2 vertex really, unless okay, except so because if it has a degree 2 vertex, any cycle that contains this will contain both of this, right? Any cycle that contains this vertex, because it's degree 2, will necessarily contain both these vertices. So maybe these two vertices can play that role of feedback vertex set. So maybe get rid of them. If you get rid of it, you have a problem. You lose this cycle, right? I can't get rid of this vertex. I mean, like we did here, we can say, oh, this vertex covers a cycle that is covered by these two vertices anyway. So why don't we get rid of it? The problem is that you even lose the cycle structure, right? So for example, if I have a graph like this, maybe make this. If I get rid of this vertex with the possible flawed argument that, oh, any cycle that contains this will contain this or this, so they can cover this, right? So if I get rid of this, then what I have is this, and your feedback vertex set may pick this to cover, or maybe pick these two vertices to cover the cycles here, but your original cycle is left uncovered. So you don't want to lose the cycle structure, okay? So what you can do is like what you said, to what is called short circuit that vertex. So what you do, if X has exactly two neighbors Y and Z, delete X and add the edge YZ. So that means if I have exactly two neighbors, I will delete it but add this edge. Okay?
This already exists there.
Add that edge also. Now your graph will become a multi-graph, that's okay. Okay? Because then I preserve the cycle structure, right? So in this case, it will be like this. So I need to cover this cycle is captured here in this thing, in this reduced graph. Now you can argue a k size thing will, if and only if there is a k size, because this cycle, 2 cycle has to be covered, which is equivalent to covering this 3 cycle. Okay, so exactly two neighbors Y and Z, delete X and add the edge YZ. So this is very important. Sometimes it's tempting to do something like deleting it, but you should notice the fact that you have not, you should capture the soundness of the rule. So what, if you just keep doing this rule on a cycle, what happens? Suppose the whole graph is a cycle. If you keep applying this rule,
You will end up with a two cycle. This one.
you can do apply that also again, right? You get a loop, right? I mean, Y and Z need not be, yeah, so they need not be distinct. Okay, so you end up with the 2 cycle, okay, let's say. Then I know I will contract it again, which means that this is my X and maybe this is Y and Z. Okay, I'll end up with the 2 cycle. So what we'll do is,
Check if it is part of it.
yeah, so if both, I mean if this is the whole graph, then I can even replace it, make it into a single loop. Okay. Let me make that as an explicit rule, right? If xy is a double edge and is an isolated component, I can actually do better. What can I do? Delete it.
One of the vertices, reduce k by 1. Delete the edge and reduce
Yeah.
k by 1. One of the vertices.
I mean, it's an isolated component. You can delete both. Right? The whole thing is a cycle. So
You can add that X to S.
exactly, that's what he means by reduce your budget, right? Then add x or y, doesn't matter, to solution S, and k becomes k minus 1, and delete x and y. Other, yeah. So your graph in general can become a multi-graph, right? So it can even, if there is a loop on x, same thing, right? Add x to S and your k becomes k minus 1. What you have several parallel edges between a pair of vertices. What can you do?
Even if it is the isolated component, same thing you can.
Yeah. So no, but I don't know. There may be a lot of edges coming out here, but some, because it's a general multi-graph, I have this.
Yeah, it is a component, isolated component.
No, it's not, because there are more things out here.
Change it to a 2 cycle.
Change it to a 2 cycle. If there are 10 parallel edges, then I won't play any role. Anyway, to cover this cycle, you have to pick x or y. So capture that information to keep 1 2 cycle out there. Everything else can be removed, right? Okay, so you can apply these rules. Now what happens to the minimum degree of the graph? So you keep applying these rules as long as possible. What happens to the minimum degree? Or I mean, what can you say about the graph? Right, so resulting graph what can you say?
Greater than or equal to 2.
2 is not possible. If it's 2, you have done something. If it has exactly 2 neighbors, you would have removed it, done some short circuiting, done something.
But that loop is there.
That loop is there, you would have picked it. If there is a loop on x, add x to s, you would have deleted it. Right? Delete x. It k becomes k minus 1. So the minimum degree is actually greater than or equal to 3. Because whenever you have degree 2 vertex, you will remove this and do short circuiting. And if you have a degree 2 vertex there, you will keep on doing this. Right. So whole thing might become a loop. In that case, you will pick it into the solution and move on. As long as it's a degree greater than or equal to 3, then you will stop. So it is a multi-graph. It can be a multi-graph with at most 2 parallel edges between any pair of vertices, and the minimum degree is at least 3. Okay. Now you can say some interesting observations.
Can you convert this multigraph back to a graph?
You may not be able to, but you can convert a k-sized feedback vertex set to a k-sized feedback vertex of the original graph. That's what you care about, right? If at the end of every rule, you have to prove this correctness, that if there is a k-sized feedback vertex set in the original graph, you will have one, right? So one direction would be obvious. To convert it back, you have to have this conversion back, right? That feedback vertex set will not pick any such vertex, would be the proof for this step. And when you go to this step, if it picked this, you know that you will pick one of these vertices, and that would be the argument for this. So you have to prove this. So you can always convert a feedback vertex set here. So this is an equivalent instance in the sense S if and only if S with minimum degree at least 3. Okay, we still have a long way to get a poly in k-sized graph, but in some special case, suppose max degree is some d. Then I want to give a kernel here in as a function of d and k. Okay. So in the case of this buzz kernelization, what we managed to do is we somehow managed to bound the max degree by k, because if it is greater than k, we had a rule to get rid of it. Finally, we had the max degree was k, and that immediately gave us a k square kernel for the number of vertices, because you want k vertices need to cover them, and so it's at most k square. Here the argument is not that easy because you are trying to cover cycles, and you also need the fact that its minimum degree is at least 3. Right. So then if size of vertex set is greater than or equal to some, well, it's a question mark, we will derive this, then we can say no. So we will prove this, that S instances are bounded. So that means if you see so many vertices, you can right away say no, and otherwise you have a kernel of size at most something like dk. So why is this? Let's try and prove this, right? So what I don't know what this constant is. What is this function? We will, and the proof will tell you. Claim G has minimum degree delta greater than or equal to 3, maximum degree at most d, and you apply these rules. Okay, so this is the claim. Let G have minimum degree delta greater than or equal to 3, max degree at most d, and has a feedback vertex set of size at most k, then something, some function of d and k. Okay, we will see what it is, we will derive it in the proof. Okay, it will be like dk essentially. So which means that if you have a rule to handle vertices with degree more than some ck, then you have a k-square sized kernel. Okay, so both would be something like order dk is what I am going to show. This is the claim. Okay, exactly what it is we will figure out. So what this suggests is if I am aiming for a k-square sized kernel, then you need a reduction rule to handle vertices with degree more than some ck. That will be the rule which requires all this heavy duty combinatorial theorems to get rid of them. But let us try and prove this. So G is an S instance, right? So there is a, let S so this is my S and this is my V minus S. And let's look at these edges and call it F. We will try and give a bound for the size of F in two ways, and out of this will my that claim will pop out. Okay, so how many edges are there? Okay, number of edges is at most cardinality of S times D, right? So this is at most k times D because there are k vertices here. Each one has degree at most D. Some of them may be inside, but even at the conservative estimate that all of them are going across, this is at most k times D. I want to give an upper bound using the minimum degree bound. So how many edges are going across here? Well, each vertex here has degree at least 3. So it's at least, so let me actually keep it like this. Yeah. So it's at least delta into size of V minus S. But I can't say it's at least that much because a lot of edges may be inside. Can a lot of edges be inside? Why not?
At most E minus S minus 1.
Yeah, why? Because this is a forest. Since S is a feedback vertex set, at most V minus S minus 1 edges can be inside, so everything else has to be outside. So this bound is at least delta into V minus S minus V minus S minus 1. Now your bound for V should follow out of this. Okay. So what is this? Delta minus 1 into V plus 1 is greater than or equal to size of S times T. Is it correct? Minus cardinality of S, so it's delta minus 1, yes. So let's take all of this there. So my cardinality of V is less than or equal to S into D plus delta minus 1 by delta minus 1. Maybe I can plug in delta equal to at least 3 or something. So, this is basically cardinality of S into D by delta minus 1. This one, yeah, okay. So, I am counting these edges in both ways, right. In the first, we said it's cardinality of S times D. Going this direction, we are going to say, since each vertex has degree at least little delta, so total degree, there is a 2 times, okay, I should subtract. Good, I remembered something from, right. So, delta times V minus S is the total degree out of all these vertices, out of which at most V minus S minus 1 edges are inside here. Why? Because this is a forest, because this is a feedback vertex set, this is a forest. So, okay, so this is correct, okay, right. Out of this delta into V minus S, edges that could be going out at most, at least, totally. Some of them are inside, some of them are outside. It is the min degree, it is the min degree. At least delta, because min degree is delta means what? Every vertex has at least delta edges coming out of it. It is the min degree, right? But out of which at most so much may be inside, so everything else has to be outside. So at most this many are inside because this is a forest. So the remaining must be, so this is it, yeah. So if delta equal to 3, what is this saying? Cardinality of S into D by 2. If delta is more, then it's even a smaller fraction. Okay, so it's 1 by delta minus 1. So this is, yeah. Isn't there a 2 here? I'm wondering because right. So edges inside are counted twice when you count the degree. So the total degree is delta times this, out of which you discount at most 2 times the degree, the remaining guys will be going out. Yeah. Right, because the remaining guys are counted only once because the other endpoint is there. So let me make it, good, delta minus 2, because delta is not 2 should play a role. Plus 2. So this is less than or equal to delta plus delta minus 2 by delta minus 2. Yes. So that's, let me rewrite it again. So if it is an S instance, if there is a feedback vertex set of size at most k, then the number of vertices in the graph is, yeah, cardinality of S into D by delta minus 2 plus cardinality of S. So it's essentially cardinality of S into D plus 1. So when D is equal to 3, the denominator is 1, and if you go even more, it's even smaller. So it's cardinality of S into D plus 1. So it's K into D plus 1. and number of edges in the graph is at most, let's now say at most d times k incident on these guys, that includes inside and outside, plus the forest, right? So number of vertices minus. So number of edges would be d times k plus and since V is bounded by S, d plus 1 times S, so it's d times S. So it's at most dk plus dk minus 1 because this is so 2 dk minus 1. Yep. Can you explain the 2 here? Is that the question?
Yes.
Yeah. So I want to count the number of edges here. I want to give a lower bound for it, right? So what do? I sum the degrees of every vertex here. And that I know is at least delta times V minus S because each vertex is degree at least delta times V minus S. This is just a sum of the degrees, out of which at most 2 times the number of edges degrees are absorbed inside because the number of edges here is V minus S minus 1 at most and every edge is counted twice in this degree, right? It's counted here as well as here. So the total degree out with the other endpoint in S would be at least delta into V minus S minus 2 times V minus S minus 1. Just think in terms of degrees and then you will see the degrees where only one endpoint is here is at least this much. And this is because this is a forest, right? So I should keep in mind that this is a forest because this is a feedback vertex. Okay, now this is it on the feedback vertex set kernel for now. All I have shown is that if you can give me a bound and a maximum degree, then I can give you a kernel which is a function of the degree and k. So in particular, if you have a nice rule to deal with high degree vertices, you get some poly in k kernel, okay. But now that I have this result here, let me now move on to giving an FPT algorithm for feedback vertex set. Okay. So now we will move on from kernelization, but now kernelization, recall, is the process of taking the input, parameterized input, in polynomial time you want to reduce it to an equivalent instance where the instance size is a function of k. Okay. We are not at this point worried about solving the problem in fixed parameter tractable time because it can be done, because we proved a theorem that if you can, I mean it's fairly obvious that if you can reduce it in poly time, this is an equivalent instance. Now your problem boils down to checking whether this is an S instance. Do any brute force algorithm. Since size of x prime is a function of k, this brute force algorithm will take some function of k time. So it fits into the fixed parameter tractable definition, which is you want an algorithm whose running time is some polynomial in the input size plus a function of k or multiplied by function of k. We showed that both are equivalent, so you can solve it. But that may not necessarily be the best FPT algorithm, right? You may have other ways to improve the fixed parameter tractable algorithm. So let's get on to what are other techniques. To kernelization is an equivalent notion, but kernelize and then use brute force may not necessarily give you the best fixed parameter tractable algorithm. So what are other techniques? And that takes us to this notion of bounded search trees. Okay, the k-square kernel for feedback vertex set, we will get to it some other time because it requires a couple of lectures carefully with all the proofs and so on. So in bounded search trees, what we do is we will try all solutions in some sense, but in a very carefully pruned way. So let's try vertex cover first and then we will get to feedback vertex set. So if I want an FPT algorithm for vertex cover, you want to know whether there is a k-sized solution. You can always kernelize because it does not cost you much, it is polynomial time. So if you want, you can kernelize it. So you get a G prime K prime where okay, now you want to solve it. You want to know whether this is an S instance. So a brute force algorithm, is there a solution of size k for vertex cover would be try all subsets of size k, check whether it covers all the edges. That will be like an n choose k times some polynomial. Since the n is at most 2k, it will be like a 2k choose k, right. So try all subsets. Would be like 2k choose k times some poly in k, and 2k choose k is roughly 4 power k. So you have an algorithm whose running time is some 4 power k times polynomial in n to actually solve and answer the question, is there a vertex cover of size at most k? But can you do better? Okay. This is one approach through the kernelization, but can we do better? Yes, there are some nice simple branching algorithm for testing whether there is a k-sized vertex cover. And what you do is you pick any edge in the graph, u or v must be in any vertex cover. We just picked one edge, u or v must be in any vertex cover, k-sized vertex cover, minimum vertex cover, whatever, it must be there anywhere. So try one by one. Would be let uv be an edge, check if vertex cover of g minus v k minus 1, then return yes. So what is it saying? Is there a vertex cover of size k minus 1 in the graph you obtain after removing v? Right? Because I'm just going to say, let me try and include v into my solution because one of this must be there. So let me try v, take it and say in the remaining graph, is there a vertex cover of size k minus 1 recursively? And if this it comes back and says yes, then I've got that k minus 1 plus this is a k-sized vertex cover. If it says no, try the other vertex. And if that also fails, you just come back and say there is no vertex cover of size at most k. So basically what we are trying is exploring all vertex covers containing u, all vertex covers containing v, and if either of them makes me lose the budget, I need to choose more than k, I will say no. Okay. So there is a tail condition. What if there is no edge in the graph at all? then if k is greater than or equal to 1, whatever, if k is greater than or equal to 0, you say yes, no problem, I can cover it with 0 or more vertices because there are no edges, otherwise, yeah. So in either, yeah. So now how much time does this algorithm take? Sorry? 2 to the power size of the number of edges. Okay. So the Bailey condition would be if k is equal to 0, then do something, right? If there are edges in the graph, if k has become 0, you will say then we'll return no, else yes. Okay. So 2 to the power is correct. It's a good start because it's a two-way branch, right? So imagine in my solution I have a gk where I try u or v, and it goes on. What is the height of this tree? K. Because k drops at each level, the moment k equal to 0, you are going to get out and do something. So this algorithm, and in each node you are spending some polynomial time, looking for an edge, picking a vertex, deleting it. These are all some trivial, maybe, linear time. So this is like a 2 power k algorithm, 2 power k times some small improving from n to the k. You can do it before kernelization, after kernelization doesn't matter. If you do it after kernelization, the n becomes k, but you have spent some polynomial time before. Now the reason I wanted to mention this, I'm sure most of you have seen this algorithm, is that if I want to apply this for feedback vertex set, what do I do? Because I have that result in the board, I want to say that and then stop. If I want to apply this for feedback vertex set, the reason this gives me a two-way branch is because my edge has two vertices, and I know that any cover should pick at least one of these vertices. So I try this or try that. If I want to apply a similar algorithm for feedback vertex set, what should be the structure on which to branch? Cycle, right? If I find a cycle in the graph, then I know that I have to pick one of these vertices, at least one of these vertices in my cover. So I can do this branching, not two-way, but the height would be k, because k would drop at each step, but it won't be two-way because it will be the length of the cycle. Now I can't guarantee the length of the cycle. Ideally I want something constant to get a c power k algorithm, right? But in general, the cycle length can be n by 2 whole thing. But since we have ensured that the minimum degree is at least 3 by this polynomial time pre-processing, we can show that there is a short cycle. Okay. There is a result due to who else? Eridosh and Posa, I think, which says that any minimum degree 3 graph has girth. This is length of the shortest cycle. At most log n or 2 log n on n vertices, right? And what is nice is you can also find it in linear time. Okay, so if your graph has no degree 2 vertices, then if it has a cycle at all, the minimum degree is, so if the minimum degree is delta, the delta will come in the base, delta or delta minus 1. Okay. So, exercise 1, try and prove this, pretty easy. Now, if I have this, does that help my branching algorithm? So, what do I do now? I find such a cycle and then do the branching. I know that at least one of the vertices must be in any feedback vertex set. So, what sort of a running time would I get? Log n to the power k, right? This was 2 power k because it's a two-way branching to a height k. The height will remain k because once I pick a vertex and delete it, now in the remaining graph, I will look for a feedback vertex set of size k minus 1. But I have so many choices now. Log n power k, so the exercise 2, log n power k doesn't look like an FPT running time, right? Because it is not f of k times polynomial in n. But actually it is. That's exercise number 2. Show that for some function f, some constant d. Okay, so we'll start with this and go deeper into bounded search trees, all kinds of recurrences, how to solve them and all that. So, that will be the next topic.